Ever thought about why time flies when having fun but drags when bored? Imagine if this wasn't just a psychological phenomenon, but a physical one. Intriguing, isn't it? This is where we begin our journey into the vast expanse of time and space. Time, as we perceive it, is a constant. Each second ticks by with relentless precision. But what if I told you that time could waver, could stretch and contract? This isn't a flight of fancy or a whimsical thought, but a concept deeply rooted in the fabric of our universe. A notion brought into light by one of the greatest minds of the 20th century, Albert Einstein. He proposed the theory of relativity, a groundbreaking perspective that challenged our understanding of time, space, and gravity. So, is time truly as steadfast as we believe? Or does it dance to the melody of the cosmos? Now, hold on to your seats as we dive into the intriguing world of time dilation. Scene script. Time, as we know it, might not be as absolute as we think. Imagine you're in a world where time doesn't tick at the same pace for everyone. Sounds like a sci-fi movie plot, right? Well, it's not. This is the world as described by Albert Einstein in his theory of relativity. Einstein proposed that time isn't a fixed entity. It's a relative concept, meaning it can vary depending on the observer's movement and gravitational field. To better understand this, let's consider the famous thought experiment of the twins. So imagine two twins. Let's call them Alice and Bob. Alice decides to embark on an epic journey through space, traveling at nearly the speed of light. Bob, on the other hand, chooses to stay back on Earth, living a regular life. Now, according to the rules of our everyday world, we'd expect both Alice and Bob to age at the same rate, right? But here's where things get interesting. Einstein's theory suggests otherwise. Since Alice is traveling at such extreme speeds, her time would actually slow down relative to Bob's. Yes, you heard that right. Time would pass slower for Alice than it would for Bob. When Alice returns from her cosmic journey, she'd find that Bob has aged significantly more than her. This might sound fantastical, but it's not just theoretical. Scientists have actually tested this with precise atomic clocks, one placed on a fast-moving jet and another kept on Earth. The results? Exactly as Einstein predicted. The clock on the jet lagged behind the one on Earth. So in the universe, according to Einstein, time isn't a one-size-fits-all concept. It's flexible, stretchable, and squeezable. It's like a cosmic fabric, warping and bending under the influence of speed and gravity. So, according to Einstein, time can stretch and squeeze depending on your speed and gravity. But how does this happen? Welcome to the world of time dilation, where time can stretch like a rubber band. Imagine you're on a spaceship traveling close to the speed of light. On board, you have a special kind of clock, a light clock, which ticks every time a beam of light bounces between two mirrors. To you, inside the spaceship, the light appears to travel straight up and down. But to an observer outside your spaceship, the light appears to travel in a diagonal path because of your ship's motion. This is where things get interesting. Because the speed of light is always constant, this means that the light in your spaceship must travel a longer distance for the outside observer compared to you inside the spaceship. And since the speed of light is always the same, a longer distance means a longer time. This is the essence of time dilation. As you speed up, time for you slows down compared to someone who is stationary. But hold on, this is not just a theoretical concept. It's been proven through countless experiments, like the one with atomic clocks flown around the Earth, which came back showing a slightly different time than the stationary ones. This is not because the clocks were faulty, but because time itself stretched due to their high speed. So, to sum up, time dilation is this strange but real phenomenon where time can stretch and contract depending on how fast you're moving. The faster you go, the more time stretches for you, and the slower it seems to pass compared to someone who is stationary. This might sound like something out of a science fiction novel, but it's all thanks to a young patent clerk named Albert Einstein and his theory of relativity. His revolutionary idea that the laws of physics should look the same for all observers, no matter their speed or direction, led to this fascinating exploration of time and space. So the faster you move, the slower your time passes compared to someone who is stationary. But how does gravity fit into this? Imagine dropping a clock into a black hole. What happens to the time on that clock? Welcome to the world of gravitational time dilation, a fascinating corollary of Einstein's theory of relativity. As we delve deeper into this concept, you'll see how gravity, that invisible force keeping us grounded, has a profound effect on time. In essence, gravitational time dilation is the idea that time runs slower in stronger gravitational fields. Picture a clock at sea level and another at the peak of Mount Everest. According to the theory of relativity, the clock at sea level ticks slower than the one on the mountain. Why? Simply put, the clock at sea level is closer to the center of the Earth, hence in a stronger gravitational field. The difference may be minuscule, something we wouldn't notice in our day-to-day lives, but it becomes significant when we consider high-precision systems, such as the Global Positioning System. Now, let's talk about the GPS. It's a network of about 24 satellites orbiting Earth, providing us with precise geographical information. These satellites carry extremely accurate atomic clocks. But here's the twist. These clocks, being farther from Earth's gravitational pull, tick faster than the clocks on Earth's surface. If this wasn't accounted for, our GPS systems would be off by about 2 kilometers each day. Yes, you heard that right, 2 kilometers. So how do we handle this? The system is calibrated to correct for this time dilation effect, ensuring that the time displayed on our devices matches the time on Earth, despite the difference in gravity. To sum it up, gravitational time dilation is a striking demonstration of how gravity influences time. It's an abstract concept that has tangible implications in our world. It's why we can navigate our way using GPS. And it's why our imaginary clock, if thrown into a black hole, would seem to slow down and eventually stop as it approaches the event horizon. So the stronger the gravity, the slower the time. Now that's a heavy concept. Time dilation, a concept straight out of science fiction, is actually a part of our reality. Let's take a moment to reflect on the fascinating concept we've been exploring. Time dilation, in essence, is the stretching of time. But it isn't a one-size-fits-all phenomenon. It's influenced by two primary factors, speed and gravity. Imagine you're aboard a spaceship, traveling at near light speed. As you zip through the cosmos, time inside your spaceship slows down compared to the time experienced by those left behind on Earth. This is called relative velocity time dilation, a concept which is a direct consequence of Einstein's theory of special relativity. Now, let's bring gravity into the equation. If your spaceship were to hover near a massive object, say a black hole, time would slow down even more. This is gravitational time dilation, a prediction of Einstein's theory of general relativity. In both instances, time is not absolute. It dilates, it stretches, it bends to the will of speed and gravity. But what does this mean for us, living our lives on planet Earth? Well, it means that time dilation is not just a theoretical concept. It's real and it's happening, even if on a scale so minuscule that we don't notice it in our day-to-day lives. For instance, clocks on GPS satellites orbiting Earth run slightly faster than clocks on the surface due to the lesser gravitational pull they experience. To keep our GPS system accurate, this time dilation effect has to be taken into account. In a broader sense, time dilation is a reminder of the interconnectedness of our universe. It's a testament to the fact that space, time, speed, and gravity are all intricately woven into the fabric of our reality. So, next time you feel time flying or dragging, remember it's all relative.